Greetings to all. Welcome back to the course on power electronics using MATLAB Simulink. So in this video too, we'll be learning about the diodes, MOSFETs and the BJTs and the IGBTs. So first we'll be learning about what is semiconductor. So a semiconductor or conductor or insulator, how these three are defined and how these three are being differentiated. So the basic thing which differentiate all these three things are the resistivity. So resistivity for an insulator, any element or any material which has a resistivity of more than 10 to the power 8 of ohms per centimeter, this is the unit of resistivity, ohm centimeter, qualifies as the insulator. So for example, anything glass, rubber, oil, plastic, diamond are all insulators. Anything between 10 to the power minus 4 ohm centimeter and 10 to the power 8 centimeter ohm centimeter qualifies as the semiconductor. So these are silicon, germanium and selenium. These are the, and these all have a special quality. They all fall in group 4. What is group 4? In a periodic table, in a, when you have learned your chemistry lessons, in group 4 these are all situated, these elements are all situated in group 4. And anything having a resistivity of less than 10 to the power 4 ohm centimeter qualifies as a conductor, like gold, silver, copper, iron, aluminum, etc. Mainly all the metals comes in this category. So metals are good conductors. So this is the difference between the conductor, semiconductor and insulator, and these are the on the basis of the electrical resistivity. Then let's deep down into the p-type and the n-type semiconductors. Semiconductors are divided into two parts. What happened? This is a group 4 of the periodic table. So here you can see one is carbon, silicon, germanium and selenium. So most of the time we are using silicon. So silicon, if you remember, the silicon has 4 electrons in its outermost ring. Okay, so it has 4 electrons. So I am marking here 4 electrons like cross. So these are the 4 electrons. And whenever there is a doping of phosphorus or a group 5 into the silicon in the group 4, whenever the group 5 doping is done in the group 4, the semiconductor becomes n-type. N-type means it now contains more electron than the holes. So what happen is, let me give you a very easy example. The outermost ring of group 4 should have 8 electrons. So 8 electrons, I mean 1, 2, 3, 4, but actually it has only 4 electrons. So rest 4 can be considered as holes. So that means each group 4 element will be having 4 electrons and 4 holes. But whenever the doping of phosphorus is done to the silicon or the group 5 is done to the group 4, then there are more number of electrons. Electrons exceeds holes. Similarly for p-type, if group 3 is doped into group 4, then there are holes more than electrons. Okay, this is a basic difference between the p-type and the n-type. P means positive, positive means holes, and n means negative, negative means electron. So this is one thing. So single element silicon germanium is a simple semiconductor. Now compound is when we combine 3 or 4 with 5 doping, 5 with 3 doping, whatever case may be. So there are compounds also. So most of the time when you are dealing with a diode, it is mostly a silicon or germanium diode. But when you are dealing with MOSFET, IGBT, then we are using compound heavily. Now what are the types of diode? So diode can be depending on the p-n junction. So what is a diode? Diode consists of a p-type and n-type semiconductor. So this is a p-type and this is a n-type. And because of these two combination, there exists a depletion layer between them. This is a depletion layer. So we will not be going into the physics of diodes, but we'll be learning that there is a depletion layer between p and n junction, and whenever there is a positive attached to the p type and negative attached to the n side, this depletion layer squeezes and the current starts to flow. So this will flow when p is connected to the positive and n is connected to the negative. Whenever the opposite happens, means this is p and p is connected to negative and n is connected to positive, this depletion layer widens and therefore blocks voltage. So this is a diode symbol, and that is why it is shown with the arrow that current will flow in this direction, and in this direction it will not flow. So on the basis of junction, that PN junction, there are these much types of diode. One is general purpose diode, one is fast recovery diode, one is TVS diode, Zener diode, variable capacitance diode and high frequency diode. Then there are metal semiconductor junction diode also. This means that at one portion they might be having n-type and other portion is metal. So these are the type of diode which do not have p-n junction. They have a some p or metal junction or n or metal junction. So these are Schottky diodes, high frequency Schottky diodes. So mainly these are Schottky diodes. They are known as Schottky diodes. So what is the characteristic of diode characteristic? So in this is p and this is n. This small portion depicted by n. Okay. So whenever this is the AC, so what this AC looks like is it goes positive and negative. This is, so for the first cycle, when the voltage is positive, this will be on. So it is known as forward bias. Whenever the P is connected to the positive and N is connected to the negative, the voltage goes into forward bias mode. And for the forward bias mode, it conducts. So here it is conducting. This is forward bias. For forward bias, this cut-in voltage is very important. As you can see here, at more than slightly more than 0.5 voltage, the diode starts to conduct. Before that, it was not conducting. Before that, the current was zero. Why it was zero? Because this is known as a cut-in voltage. This is the minimum voltage, forward voltage required to turn on the diode. And for silicon, it is 0.7 volt. For germanium, it is slightly higher. Similarly, in the reverse bias case, whenever the reverse case is coming, this is the second part. Whenever the reverse voltage is coming, that means negative to the P side and positive to the N side. This will block and this will block the voltage. So the diode will be acting as a off switch. In this you can see there is no current flowing here. But there is a certain current at the reverse breakdown voltage. So there is a breakdown voltage up to which diode can handle the reverse voltage. After that it will just break down. So this blue one is showing breakdown. This is showing breakdown. Breakdown means now the diode is not working, it is being destroyed. So this breakdown is a reverse voltage which diode, up to which diode can sustain. Then there are fast recovery diode. What are fast recovery diode? Whenever a diode is switched on and off, there is a certain amount of period diode required to recover. What is recovery means? This is a diode. This is a PN junction. And suppose it is on and the current is flowing through it. So the current is flowing through it. So the flow of current can be marked as flow of electrons in the holes. As soon as you switch off it, by switching off I mean you are putting negative here and positive here. What happens? The depletion layer needs to get intact or needs to get rebuilt, because during the forward bias the junction gets very narrow, so that the flow of electron and holes can happen. But as soon as you switch off the voltage or as soon as you switch off the diode, this junction need to be widened. And for this the diode required a certain amount of time. That time is known as the recombination time or the total recovery time or the TRR of the diode. So here you can see for a normal diode this TRR is certain amount. This is shown by TRR. This is the TRR. So for a very fast recovery diode, this TRR should be in the range of 0 up to 100 nanosecond. For a general diode it can be 50 microsecond. Up to 50 microsecond. Also the forward voltage drop is 0.9. What is the difference between fast recovery diode and general recovery diode is on the basis of the total recovery time. So if the total recovery time is very less, in the range of few hundred of nanosecond or few tens of nanosecond, then it is qualified as a fast recovery diode. Otherwise, if the recovery time is more than 100 nanosecond or it is in a range of microsecond, then we consider it as a general diode. So why fast recovery diode are used? It is used for very high frequency switching. So if a device or the power electronics converter is working at a say 100 kilohertz of operating frequency or switching frequency, then we require a fast recovery diode, because with 100 kilohertz we will having a very in few tens of microsecond we need all the switchings to be done. And for a moderate kilo, if we are working in a motor drive system or in a basic rectifier or a converter, then we can go with a general purpose diode. Now there is special, when coming to the fast recovery, there is a special diode known as Schottky diode. So Schottky diode, what is the difference between Schottky diode? It is a metal semiconductor junction diode offering a fast switching speed at low forward voltage drop. So a Schottky diode consists of a semiconductor plus a metal. So both are combined and this gives rise to the very low cut-in voltage. Cut-in voltage is when the current flow starts at the voltage where the forward bias shows or where the forward bias is actually working. These are also used in very high switching, like 50 gigahertz switching, and the majority carrier relies on the mostly on the electron, and that's why it is very fast. There's a reverse voltage also. So this plot shows a difference between a normal PN junction diode and a Schottky diode. So you can see that a PN junction diode has a higher cut-in voltage. This is higher cut-in voltage, and this blue one is showing a Schottky. So the Schottky will have a reverse breakdown voltage of very less, while the PN junction has a wider junction, and that is why it will have a very large breakdown voltage. So these are the two different fast recovery diode and Schottky diode, two used in the similar space, means fast switching. For fast switching we can use fast recovery diode also and Schottky diode also, but depending on the application we'll be choosing one of them. The Schottky diode do not have that much power rating as fast recovery diode. So this is the difference between a Schottky diode and the fast recovery diode. They both look same because both are used for a very fast recovery of the diode, but they both are different in terms of structure also. So a metal semiconductor junction is there in Schottky diode, while a PN junction is there in recovery or fast recovery diode. Similarly, the forward voltage drop is very low in Schottky diode, while it is very decent in PN junction diode, 1.3 to 3.6 volt. These are very ultra fast diodes, Schottky diodes, and these are fast. So mainly they are the faster are Schottky diode are the more quick diodes, but they have a low voltage rating. They are up to only 200 volt, and this can be for fast recovery diode can have a voltage or the reverse blocking voltage up to 1000 volt. So wherever you need a very high speed and a low voltage circuit, then you will be going for the Schottky diode, and if a voltage is high rating and you require a fast switching, then you will be going with the fast recovery diode. So it is suitable up to 100 kilohertz, and this is up to gigahertz level. So you can see that for a small electronic circuit working on a RF level or radio frequency, you will be going with the Schottky diode, and for a power system, inverter, motor drives, you will be going with the fast recovery diode. So these are the two main diodes which are used: fast recovery diode, Schottky diode, and general purpose diode. So three diodes we have read right now. Now we'll be going through the Zener diode. So Zener diode is designed to operate in the breakdown region. So this is a special type of diode which works in the breakdown region. Earlier we have seen that this is a breakdown region, and usually diodes do not work here. So where the diodes are working in the forward voltage or up to this region. So this is a region where diodes are mostly working. But this special diode, or the diode, the last two diode which we will be learning or which we will be studying are, they both work around breakdown voltage or reverse breakdown voltage. So let's go to, so this is a Zener diode, and it works on the breakdown voltage. So why Zener diodes are used? So Zener diodes are used for providing a constant voltage. What happens whenever a negative voltage is given to the diode, there is a breakdown. But there is a good thing about breakdown, that it blocks the voltage across diode to a fixed level. So if a Zener diode having a breakdown voltage of 10 volt and you put it around a circuit, this is a Zener diode symbol. We will be writing a small z, and this is a load. So suppose this battery is giving a variable voltage between 8 volt to 12 volt, and you do not want your output voltage to exceed 10 volt. So I'll be putting here a Zener diode which is having a breakdown voltage of 10 volt. So whenever the voltage is less than 10 volt, the voltage here will be less than 10 volt, and as soon as it exceeds the 10 volt, the output will fix at the 10 volt. So Zener diode are mostly used for the constant voltage supplies. So these are reliable, and they are mostly used for the voltage regulation system. So there are two type of breakdown. If a breakdown is voltage is less than 5.6, then Zener effect. These are the two effects by which breakdown can happen. So this is a Zener breakdown and this is a avalanche breakdown. So we will be working on a Zener breakdown, or the which is a what is the difference between avalanche breakdown and Zener breakdown is, Zener breakdown is a much simpler, or not simpler, much the avalanche breakdown is the actual breakdown where the recovery is very tough. So we'll be working, so most of the Zener diode which are on low voltage works on the Zener effect. This is a symbol. A symbol is a very simple. You have a diode and you just make a symbol like Z across the diode. So this is a Zener diode. Now another diode is transient voltage suppression diode, or TVS diode. This has a similar working. They both, Zener diode and TVS diode, work on the breakdown region, but there is a very small difference between both of these diode. One of the main differences is transient voltage suppression diode do not used for voltage regulation. They are actually put there to protect the circuit. So there are two circuit. This is an IC. Here you can see there's a power supply. Whenever everything is going okay, these TVS diode are off, and the IC driver is given a fixed voltage of say 5 volt. But as soon as there is a over voltage means any amount of over voltage can be there. It can be 100 volt surge also. As soon as it hits above the TVS breakdown, all the energy will be transmitted through the TVS, and to the IC will be giving only 5 volt. So what happened, it is mostly used for protections, and there is a high amount of energy which it can take at one given moment. So it is a surge protector. So whenever a very high surge, a 5 volt circuit, if given a small impulse of 100 volt, can be destroyed. So what happened, this TVS diode protects it from that plus 95 voltage which is coming abruptly to the circuit. So all of this voltage will be blocked at the TVS, and the energy or the extra current which is coming will be bypassed through the TVS diode. So TVS is a more of a protection diode, and its symbol is shown here. This is how the symbol is made, with a gap between them. So TVS and Zener diode are two similar looking diode, but they have a very different application. And also TVS diode can work on forward reverse in both ways. So this is a TVS diode connected back to back, so they can block voltage in both directions. So this is a very good example where you can see that a TVS diode is used. So this is the voltage I require in a circuit. This is the voltage. So as soon as the surge is coming, this surge has been absorbed by the TVS. So this is a surge which is being absorbed. While Zener diode is very different. Zener diode, the voltage I need is a 10 volt, and above that voltage I will be rejecting it. So both diodes have a function of clamping a certain voltage, but their usage is different. So it is used to absorb surge, and it is used to absorb the ripples in the voltage supply. The another basic difference is Zener diode is rated for a very small or a limited current rating, while TVS diode are used for the very high energy absorption. So this is one difference. So TVS versus Zener diode. TVS is a transient voltage protection diode, or there the name comes from TVS, and this is a voltage regulation or stabilization. Response type, because TVS is used for protection, it is less than 1 picosecond. Picosecond means 10 to the power minus 12 second. While Zener we do not use for protection, so it is a fair amount of microseconds it can use. Breakdown voltage is usually more than the clamping voltage is more than the breakdown voltage. Means if you want to clamp at 10 volt, the breakdown voltage will be 10 volt only, and clamping voltage can be higher also. This is precisely VZ because it is used for voltage regulation, so I need a fixed voltage. This is current handling capacity of TVS is very high. It can handle up to kiloampere because it is the thing is TVS is used for the protection. So during a surge, a very high impulse current can also come of 1 kiloampere. So it should be able to handle that current. And Zener diode, because it is not used for protection, it is usually in the range of low current in a milliampere level. So this can handle a peak power of in kilowatt range. This is in milliwatt range. So these are the two different type of Zener diodes. So this is all for this video. We'll be learning about the BJT in the next topic. Thank you.